So we have covered in the last session about the HDFS, right? So HDFS is Hadoop Distributed File System. We have discussed what NFS is, Network File System, and then we have discussed about the limitation of Network File System, then how your distributed file system overcome all those limitations that we have discussed, right? And then we have also discussed about the master-slave architecture in HDFS. The data is stored in the data node, right? And the master is a name node which actually keeps a metadata copy of all your data. So this complete architecture is a master-slave architecture. We've discussed like what name node is and what data node is. We have discussed two approaches like uh, how your name node and data node interacts. We have discussed like if name node gets failed, then there are two ways you can recover it. One is you can keep a backup server using your NFS, and another way is to keep patch high availability where it where there will be a different name nodes working together. One will be active at one time and other will be on standby mode. We have also discussed like what basically is input split, how our data is stored in the data node. It is stored in the form of blocks, not in the form of files. Data is data is divided into block first, and then it is stored in your HDFS layer. And name node keeps a track like what data is present at what block. Also, the data node keeps on sending its report to name node at every 10 seconds. Data node keeps name node updated with the metadata information, and it also keeps on updating like I am active and I'm currently working. So all those activities of its own, it keeps on providing that to a name node. To which name node it provides that information depends upon the namespace ID. So every data node has a namespace ID allocated with it. So let's say in a large cluster of 500 nodes, you may have 2 to 3 name nodes. In that case, there will be 2 to 3 namespace ID. For a set of 200 data nodes, you will have one namespace ID. So those 200 data nodes will talk to that particular name node based on the namespace ID assigned. Similarly, for the other data nodes in the cluster. So why it keeps on sending the heartbeat to a name node? The reason is if let's say any of your data node corrupts, or if any of the data node does not working properly or not in a healthy state, then name node can come to know about that, and then it can move the same data copy, or it can utilize the distributed or the replicated copy of it present in a different data node. So we have already discussed about the replication policy of data. So in Hadoop, in HDFS, you will have 3 copy of your data distributed, right? So for a same data, you will have 3 copies, which is distributed across the cluster. If any of the copy gets disrupted, the other 2 copy, which is fresh and which is correct, it can be utilized. Right. Then also we have discussed about the minimal data motion. So what minimal data motion means? The minimal data motion is here what happen is the data does not move to your code. So let's say you have applied a filter logic where you want to find out all the customers who are doing a transaction more than 10,000, right? So the data is present, the transaction data is present at your HDFS layer, and you want to apply filter logic. So here, filter logic code that you have written is of 1 KB or maybe of lesser size. So if that particular code is running on your server 1, let's say, and the data is residing at server 2, server 3, and server 4, then it is easy to move that code, 1 KB of file code, to the network uh, rather than sending the data to that server 1 machine, right? So that is how Hadoop works. So Hadoop does not send the data to the network. Instead, it sends the code to the network, to the data, right? So that code is nothing called a mapper code, which goes to each machine individually and runs in parallel fashion. But that's the reason we call it as minimal data motion. Data is not moving. Today, using that PowerPoint slide, I would like to brief like where exactly you will have a data motion in Hadoop as well, right? So any queries if you guys have, then you can just ask me at any time. Rack, we have also already discussed about this. So so we'll be discussing more that on the weekends, right? Because that part is not untouched, not touched with some of you guys. So yeah. So this is how the name node keeps a copy of all the data which is present in the data node. So let's say you have a file foo, and this file is distributed, you know, uh, with a 3 copy of it. One is present at the first data node, second is present at the second data node, and the third is present at your third data node. So that's how it is distributed, right? So if let's say it basically replicated, not distributed, I would say it is basically replicated. And if any of the file or if any of the file gets disrupted, then you already have a different copy of it in a different data node present. So your code can utilize this particular copy in that case. Default block size we already discussed of HDF is 64 MB. You can configure it using your HDFS site.xml. I'll show you like how you can do that. Each block is replicated 3 number of times. So we already discussed like the replication policy in Hadoop. Again, you can change it to make it 4 and 5 as per your requirement. If you want more redundancy of data, if you want more copy of data, you can do that. And we have also used some of the HDFS and Hadoop command to see if, uh, to look all the distributed file system data. And then we have discussed a little bit about the map reduce flow, right? So today we'll be getting in more detail like how your map reduce job runs, what basically map reduce is. Uh, for the ones who don't know what MapReduce is, so in a very simpler terms, so there are two things that happens in the programming world. One is your code and another is your data. In Hadoop, these two things are divided. The data, when we talk about data, so HDFS comes. And when we talk about MapReduce, when we talk about code or the programming logic, that is the running on top of your data, then we call it as a map reduce, right? So what is basically map reduce is? Map reduce is nothing but two functions written in Java, and I'll show its uh, you know the processing, how it processes, what basically how mapper works, how reducer works, so that internal mechanism that we are going to show you. But for timing, just understand that map reduce is nothing but two functions written on a Hadoop framework, which actually helps you to write your code and your programming logic. Why we have a map reducer? Why don't we say it's a Java code? The reason is because we want to perform a distributed programming here. We are not concerned of processing the record serially one by one. We are concerned here to process the record distributed fashion. So distributed, when I say, so let's say you have 4 set of machine, and if you want to process the record parallelly, then you should have 4 processes or 4 threads running in parallel, processing the different data residing at different uh, nodes or different machines, and then writing the data intermediate output and then collating that intermediate output to get the final result. So we want everything in a parallel way, so that's the reason we are not calling it at any other Java code, right? So here we are performing the distributed programming, so we call it as a, or Hadoop name it as a mapper and reducer. So your mapper function will work parallelly for all this data, and your reducer function will collate that particular intermediate result to provide you the final result. How it does it, we'll be talking shortly on this. Right? Any queries you guys have? What HTF is, what code? Maybe there will be a lot many queries, but I think just for now we can just take of understanding. We can say that if you're talking about the data resides at your HTFS. Hadoop distributed file system. And we're talking about code and programming logic that dealt with the map reduce. Yeah, Karthik, you're about to say something?
Well, I think you'll talk later, but you said in the first class, Hive is for non-Java people, correct?
Correct, correct.
Okay.
Yeah, so when I talk about Hive, Pig, and all those tools and technologies, so that does not require Java knowledge, and there you can write a simple SQL queries which will actually convert your SQL query to your map reduce job internally. Right, so because here if I say that if you want to write your own mapper and reducer, then it really painful for the ones who are not from Java background to write their own mapper and reducer. So that is the reason they provide us some tools that we are also going to cover in the later sessions. So now this is the complete understanding. The code and the programming logic will be done in MapReduce and the data will be done in HTTPS. When I talk about data, so two things come in our mind. There is a name node and a data node. So what basically name node and what basically data node is? We already covered, but just want to give a glimpse again. The data node is nothing but your storage layer, right? So let's say you have 5 machines and 5 machines at 320 GB of hard disk. So these 320 GB hard disk into 4 is your data node. These are all your data nodes. So there are 4 data node we can call it. So 4 machine, 4 data node. And what is the name node? So name node is nothing but a master server. It can be amongst the 4 server, it can be one amongst the 4 server, or it can be a different machine altogether. So the name node and also the name node and data node can work on the same machine. So your server 1 can act as a name node and data node. Your server 2 acts as a data node, server 3 acts as a data node, and server 4 acts as a data node. So data node will keep the data, and name node will keep the metadata copy of like which particular block has which particular data, that information. And one more thing is edit log. Like if any of the block gets modified or written with a different data, then it also keeps an updated copy of it in the form of logs. Right. We'll talk more about logs, like how what edit logs is and how they are used for recovery and all. So we'll be discussing that, right? So that's how. Any queries on this code and the data? Ravi, Haima, any queries on this?
I'm fine, sir.
Yeah. Move to the presentation part. Today we have discussed, right, some the MapReduce code. So how MapReduce works, because this is the heart of Hadoop, right? To understand it, it's very important. If you understand the MapReduce, then you can you can write your own code in your Hadoop. So that's what is the agenda. So knowing it is very important, right? So that's the reason we are putting our more efforts in understanding the MapReduce. We can have 2 to 3 sessions more just to understand one thing and try it with the more scenarios so that we become more comfortable, right? So let's discuss like what exactly happened. So Karthik, can you just give me an overview like uh, what we have studied, what we have covered yesterday on MapReduce?
Okay, can you hear me?
Yes, Karthik.
So you have the input, which is a transaction file, and then you have the map, which uh, you write the code saying, uh, I think our example was list people who spend $10,000 or more. And then you have the transformation logic, I think, and then the final step is a reducer, which actually executes, I think. Is that right?
You are correct. Yes. So yeah, so we'll be looking that into more detail, like how what is more specific in Hadoop when we do the same functionality. So these kind of scenarios, they are also handled in your legacy system in a mainframe in ETL. But what makes more you know what makes it more interesting in Hadoop and why it become more faster in Hadoop? So you'll see like how it does, right? So yeah, so this basically your input file is your source file where you have a customer ID or transaction amount, the date of transaction. So you can see the data is not sorted in a customer ID, right? The data is not sorted, you are getting the 101 record at the first and then at the last as well. Data is not sorted, and the data and the transaction date is of different months. It's first of 2016, first of January, and then March and something like May. So every so for the entire year you have this kind of history of transactions for the customers. This is a very small data set just to make this a small example to make understand, right? Then so this basically an input file, right? So what happens when this input file comes, right? Your source, your business gives you an input file. What exactly happened next? It first of all stored in your HDFS layer. So it is divided into blocks. So let's say this particular file is of 128 megabyte and your default block size is 64 MB. So there will be two blocks allocated to it, right? So here it is evenly divided. You have total 8 records, 4 records in each block it gets stored. Each block is of 64 MB, right? Then you have a mapper process. Now this is till this time you have your uh, HDFS part or your data part, right? Your data is present now in HDFS. Now what you're going to do is you're performing a MapReduce function on that. What MapReduce code is? You want to find out all the customers who have done transaction more and equal to 1,000, right? So you're not considering 10,000, you're considering more than 1,000, right? So I think all the record will come in the output. Anyways, so we'll see. So now your data come at this point. There's no logic will implement it till now. The data is loaded as it is. We call this thing as a staging thing. Right? So you have just dumped the data to your staging area or your HDFS area, and now you're writing a map reduce code. So you have written your map logic. The logic says that you want to filter out all those customers who have done transaction more than 1,000. So since there are two input split, right, because for each of 64 MB and 64 MB, you have two mapper assigned to it because we have covered in the last session that your mapper task depends on the number of input split you have. So if you have two input split for input file, because input file of 128 MB, so there will be two blocks and two input splits, and you will be two mapper assigned to, right? So you can see that there are two mapper process. Then this is interesting. So a very important thing is this particular. So we are considering this example for a single machine, for a single node. There can be multiple such the same multiple same map process running in a different data node as well, and the data is distributed in all that particular data node, right? So since in this node, in the server 1, you have 64 and 61 MB two blocks. Let's say you have server 2, there also you can have 64 MB 64 MB block, and then again you have a mapper and mapper process, right? Now, so as we all know that to perform any transformation you need a RAM, because you cannot perform the transformation on the disk, right? You need to bring the data to your RAM, to your memory, and then you start performing. So there is some allocated size for each mapper process that is decided by io.sort.mb, defined in the mapper.site.xml property file. So that io.sort.mb has that limit threshold value up to which your mapper process can utilize your RAM. So let's say 4 gigabytes of RAM you have for a machine, and it says like your io.sort.mb says that it can use 32, 3.2 gigs of RAM. So it will utilize that particular RAM only, right? Because you cannot give all the RAM to a single process, to a map process. Uh, there are other processes also running at the background that also utilize the RAM. So that's a way you just set the specific value which is lesser than the size of your RAM. So that is defined in a maprit We'll see how we can define that in later sessions. Right, once you set that, and your mapper process start performing the transformation logic. That is the transaction, the customer doing the transaction more than 1,000. And and one more thing which is important here is as and when your mapper process utilize your 80% of that io.map, io.sort.mb value, it start writing the data to your disk, and that is the intermediate data. So that intermediate data will have all the customers uh, doing transactions, right? Yeah. So this is the way it starts filling the disk as and when it gets 80% above. And one more thing here is very interesting. If you can see that the data is present in a local file system. So if this particular process is running in a server 1, then the data will be in server 1. And it is not in HDFS, it is in your local file system. And if you are running this particular same process in a different machine, then that different machine will have so the mapper output will be written in that particular machine, right? It will not return to your HDFS path. When I say HDFS, it is mix of all the data, right? So it's a spool of your old storage for all the servers. But when I say local file system, so it is specific to that server. So server 1 and server 2 and server 3 likewise. So here you see that data started spilling to disk, the intermediate output of map, and this intermediate output is basically partitioned, right, and sorted. So when I say partitioned, so what partitioning is? Partitioning is you are creating the partition so that you know the same key goes to the same partition. For example, your customer ID with 101, right, is it, can have same values, right? There can be multiple such customer ID with the same value, 101. So they will all go to the same key. Right? They'll all go to the same partition basically. So that is what we call it partition by key, and it will be sorted. So your 101 ID will come first, and then 102, and this way. So we'll talk more about this when we cover combiner, but just for time being understand like all the intermediate output of map is sent to combiner. Why we do that, we'll discuss more on that later, right? So till now we have all our data, all our mapper output or all our mapper output stored in a local file system. And then we have a different phase that is a shuffle and sort phase. Right? So what exactly happened is shuffle and sort phase. This algorithm called as merge sort that we apply. So as you can see that mapper is providing intermediate outputs. So that output is sorted now using a merge sort, right? Because the same mapper can provide a different output, right? So that is again merged and sorted. This is how it is done, right? So we can see that data is now sorted. So the first mapper input is already sorted, so you couldn't see any changes. But for the second, I think you can see that customer ID is sorted. We have 101 customer ID coming first. So this very interesting thing is here, everything is going on parallel. So this mapper process is running, is working on this particular data set in parallel, and this is also working in the different data set in parallel. So the time taken is, is very less, right? So this is how your suffer in short. So this is not the shuffle phase, this is the sort phase. So here what we call shuffling is nothing but your all the mapper output is sent to a sort, and then it is sorted. This is nothing but a shuffling, we call it a shuffle. You're shuffling it to the sort phase, right? So copying all the mapper output and then you are sorting it. That's all. Now, so as and when we have covered your sorting phase, and we know that the algorithm that is used is your merge sort. We will be implementing this particular merge sort as a part of assignments. Now, next what happens? So you have your mapper output written and it is sorted. As you know that there can be a multiple input states at each node, and hence the multiple map task is launched. Each map task will generate its own intermediate output, which will be merged and sorted. And now, so this till this time you have merged, data is merged and sorted. Now what we do is we will do a hash partitioning to different reducer based on a hash value generated. Why this is done? Why we are doing a hash partitioning and why we are writing the data to reducer? Because if you see that this standalone intermediate output is not your final output, right? Because you want some kind of summary report where you can have all this customer data reported. So this is just an intermediate result. So you want everything to be aggregated. To do that, you have a reducer in place. So how the data is sent to a reducer, that is important. So your all this data, right? All this data mapper data or mapper intermediate output goes to a reducer based on a partitioning. So here we call this partitioning is a hash partitioning. How internally happen, we'll talk about this. And one more thing, if you guys remember that I had talked that there is a data motion, right, in Hadoop as well. So here comes that data motion. So if let's say your server 1 and server 2 is running a map process, and your server 3 and server 4 has a reducer process, then the intermediate output which is placed in a local file system of server 1 and server 2 is transferred through the network and is placed in a server 3 and server 4 where your reducer process is running, right? So here you have a data motion. Whereas in previous case, if you see, the mapper process is going to your all data, right? So there is no data motion. So your code is moving to the data. Now, so you have intermediate output written. Now there will be some hash partitioning. So hash partitioning is done based on a hash function. So it, this is a function for that, the prototype function. So here you will have a key and a number of partitions. So what is a key basically? Your key is nothing but a customer ID. A number of partition is set in a configuration file, that is mapped site.xml, where you define that how many partition you want to keep. So it totally depends like how many reducer you have. So if you have two reducer if you want to use, then you can set your number of partition to 2. If you want to set 3 reducers, right, working parallel, so obviously the more the reducer you will increase, the more will be the performance. But again, so there will be more data motion, right, because the mapper output, intermediate output has to move to the network to different reducers. So there will be more data motion. So more network input output overhead. But obviously your performance will increase because reducer will increase. So the number of reducer depends on the number of partitions, right? So they are both related. In the similar way, we have input split and map relation. So the number of input split defines the number of mappers. Similarly, the number of partition defines the number of reducers. Now you have a reducer process running, right? So for each key, for it will return a hash value. So if you see, so return hash function, what it's doing is it is using the key and it's performing modulus with the number of partitions. So let's say for the sake of understanding, you have two reducer. If you have two reducers, so what it does it will take the 101 customer ID and it will mod with the 2 and see how it goes. So you'll get the first intermediate output as a hash value, that the customer ID 101 mod 2. So that will give you 1, right? The remainder. So this says that this will go to the first reducer, first partition. And then you have other two. So this will give 0, right? So 102 if you divide by, so it will go to, it will mod with 2, it will give the remainder 0. So actually, so I'm sorry that one thing I missed here. Here the hash value coming 0, it will go to first reducer, because a reducer naming is, so it's something like array. So array starts with 0, right? So here also numbering of reducer starts with 0. So your hash value generated 0 will go to the first reducer, and hash value generated 1 will go to the second reducer. Similarly, if you see 103, so 103 again will be mod by 2, so it will generate 1. So it will end up to your second reducer. Reducer 2, go to reducer 1. So what will be the output of reducer? So let's see. So we have all that 102 data there, and then reducer to output you have all the 101 data. The important point is, in the reducer you will have everything, the input is sorted and the output of reducer 1 is also sorted, whereas the reducer 2 output is also sorted. But if you see, clubbing both the reducer 1 and the reducer 2 output, you will not get the data sorted. Again, if you want to sort that, then you can club the data of reducer 1 and reducer 2, and you can explicitly write a sort logic and you can sort the data. So that's it. That gives a complete picture of your map reduce code. I hope this really helps. So any questions you guys have in this? Or if you want, we can have it tomorrow also, discuss on the same things. If it is little difficult to catch at one shot. Any queries? Karthik, Ravi, Haima?
No.
No, sir.
So we are all good. We understood the concept.
Yeah.
Okay, great.
Yeah.
talking about the assignment, right? So how much you guys are comfortable in writing your MapReduce, code in any of the, so it can be a pseudo code or it can be a any code, right? So I just want you guys to write a merge sort code. You can look into the internet like how a merge sort works, right? And you can just write a pseudo code kind of thing, just on understanding part, like what you understand basically what merge sort is, and right, and kind of pseudo code. Don't go it into the detail of programming, so that is not required. Just a kind of pseudo code, like what basically merge sort does and how it does, taking up the sample data and then you can start code. So for how much time you guys require to write this code on merge sort? Maybe Monday will be fine, right?
Yeah.
Okay, great. So,
What was the question?
so Karthik, actually, I was asking like to write the merge sort code in any of the language that you find, or you can also write a pseudo code, like how merge sort works.
Okay.
Yeah.
By when?
Monday,
Monday. Okay. So
so that will give us more understanding, better understanding. And this most of the time it is an interview question as well, like how much sort works. Yeah. So you're okay with the shuffle and sort phase, you're okay with the merge sort, and you're okay with the partitioning, right? So these are the three important concepts in the MapReduce code. The data size become huge and huge, but the process remains the same. Your code remains the same. Yeah. Just take 2 to 3 minutes and just to take a note of that, and any queries if you have, you can discuss. Yeah. So one more thing which is important here is, let's say if your source data or the data that's coming in as a source is very huge, it's very, you can also compress that. So for that, so there are two ways of compressing it. Actually, there are many such schemes. So one scheme is codec scheme. So that scheme that you can use to compress your input source data, and you can set this property to true so that you can write the data in this compressed format. So it happens like most of the time your data is a file is very huge, and you don't want to process it, as it is. So you just want to compress it first, and then you have to write. So what you do is there's compression uh, function or methods written in Java, so you just can use that particular method. I'll show you like how you can use that when we start working on a MapReduce code. So I think today we'll take up this much only, and I would just I'll forward this PowerPoint presentation to you guys so that you can just go through it once again and see if you guys come up with any queries, right? And then tomorrow we'll be working on some MapReduce code hands-on practices, right? In the meantime, I've asked you guys to have that virtual machine workstation and the AnyDesk installed. So is that get installed or we're in the process of that?
We did, sir. We did it.
So you did that, Ravi?
Yeah. Even Haima did it.
Oh, that's great. So yeah, so Karthik, have you downloaded that workstation?
Yeah, I have both.
Okay, that's great. So what I'll do is today I'll share my this Cloudera machine to you guys. Just download it at your machine, and then using the remote desktop, I'll just open it. Right. So what is the configuration, basic configuration of your machine? So it's the RAM is 4 GB above, right? Four gigs RAM size. It's more than that, right?
Yeah.
Oh, that's great. It works fine then. Because the Cloudera it takes around 2 to 3 GB. So that's all. So I think that's it for now. I'll just forward this PowerPoint presentation to you, and in meantime, just go through with the merge sort code. I Google it and just understand how merge sort works. I already shown it with an example, but if I think it will be great if you just go through it at your own, right? And if you require any help, so we'll be working on that, right? Just write a pseudocode and a merge sort. Pseudocode will do, or if you want to write in a Python or Java, I think that will also be great. Right.
Okay.
Okay, guys, then let's meet up tomorrow, same time, right?
Okay.
Okay, thank you.
Thanks.